Greetings! Welcome to Electronic Circuits 1. I am Razavi and this is lecture number 14. Today we will continue to look at the bipolar transistor and understand its properties better. We will see that it is in fact a voltage controlled device, a voltage dependent current source, and hence can operate as an amplifying device. If you remember last time we had an example in which we looked at the role of a voltage-dependent current source in an amplifier. So a bipolar transistor can do that. Now, before we go to today's lecture, let's briefly review what we covered last time. So, we said last time that a bipolar transistor consists of two p-n junctions. So, three sections of semiconductors. An N section, a P section, another N section. The device is not symmetric because, for example, we have made the doping of this section very high so that when this junction is forward biased, electrons prefer to go this way much more than holes prefer to go this way. All right. We call the bottom terminal the emitter. It emits electrons. We call this one the base, and we call this one the collector. It collects the electrons. And we saw that we have the symbol for the structure so that we don't have to draw it every time. And this arrow indicates the difference between this terminal and that terminal. So it has a meaning behind it. And then we said this device is useful only under certain conditions. Even though it's a three-terminal device and we can have many different combinations of voltages around it, positive here, negative here, etc., it's really one combination that in practice becomes useful. And that combination wants the base emitter junction to be forward biased. So we have a positive voltage here with respect to emitter, as you can see by this battery. And we want the collector base junction to be reverse biased or maybe have zero bias across it. And as we saw last time, we prefer to place a voltage source between the collector and the emitter, not between the collector and the base, to create that condition. We see that if this voltage is high enough, then the collector will be higher than the base and that junction will be reverse biased. Okay, we call this the forward active region. If we have forward bias here, reverse bias here. And then we saw that under forward bias condition, under active region operation, we have a lot of electrons going from emitter to base. I forgot to make a connection here because the emitter is heavily doped. Much more than the base. That means that when this junction is forward biased, we have a lot more electrons going this way than holes going this way. And then the base region is very thin. So when the electrons arrive into the base, they prefer to go upward to the depletion region formed around the collector base junction, rather than go through this terminal and go to the battery. So when they arrive at the edge of this depletion region, they see an electric field that wants to push them this way. So they zip through the depletion region, enter the collector, are collected by the collector, and then go to the battery. So electrons keep flowing this way, which means the conventional direction of current will be this way. So we say there's a current starting from the collector, going through the base, well, not going through the base region and coming down to the emitter. All right, so we were wondering how this current changes when we change this voltage, as long as we are forward biased for the base emitter. And our intuition says that because the current of this junction is an exponential function of its voltage, just like a p-n junction that we have seen before, perhaps the current of the collector should also be an exponential function of the base emitter voltage. After all, most of these electrons make it to the collector. So without proof, we will accept that the collector current is also an exponential function of the base emitter voltage. The equation is similar to what we had for diodes. All right, so today we want to take this equation and study it more carefully in conjunction with this structure, and of course remembering that that is the symbol. And remembering that we are in forward active region. So this junction is forward biased, this junction is reverse biased, or maybe have zero across it. Very well. So today we will do the following. We will start by looking at some basic properties of the transistor, trying to acquaint ourselves with what the transistor is like, what it does, what it cannot do. Then we'll look at terminal currents. Terminal currents simply means the currents flowing through the three terminals. We have a collector terminal, an emitter terminal, and the base terminal. We would like to have equations for these. And then we would like to talk about the concept of bias, which is a key principle behind building many of these circuits that we will study in this course. All right, so let's start with that exponential equation that I showed you. So we will look at basic properties of bipolar transistors. So we have said that when we have a certain base emitter voltage, VBE, in the forward bias condition, and we have also guaranteed that the collector base junction is not forward biased, is either reverse biased or has zero bias on it, then what we know is that the current that flows into the collector, so the current that flows this way into the collector, is given by IS X of VBE over VT minus 1. Okay, so let's look at an equation that tells us what IS is in terms of properties of the device, the semiconductor pieces that we have put together, the dimensions, that sort of thing. So here's the equation for IS. IS is equal to A. A is what? A is the area of the transistor. Remember, we had the same dependency in diodes, in PN junctions. So when we say A, we mean if we look at this in three dimensions, there's an area through which the current flows from the emitter through the base to the collector, right? That area, that cross-section area, is called A. In fact, to be more precise, sometimes we call this A sub E, and we call it emitter area. So we call this emitter area. Why? Well, because in reality, when we build the device in actual fabrication, it turns out that the emitter area is smaller than the other areas. So we have to be specific about it. But at this point, don't worry about it. Just imagine that all of these have the same area, and that's equal to some number. It could be 1 micron by 1 micron. It could be 10 microns by 10 microns, some area. Okay, the next term that we have here is Q, charge of electron, as we did for diodes. Then we have Ni squared, as we did for diodes. We had all of these terms in diodes, right? And then in the denominator, we have some other stuff. We have WB. This is called the base width, or what I called before base thickness. Base width. Base width means from here to here. That's WB. All right. Then we have the doping in the base, which we call N sub B. So this is the doping in the base, doping level in the base. So we have some doping because it's P, so maybe 10 to the 15 per cubic centimeter. That would be some number. So that's that. And there's one more factor here, D sub N, which, if you remember, is diffusivity of electrons. So that's what we need here. All right, so for our purposes, we actually don't need to memorize all of this. What we do need to remember is this, that as the cross-section area of the device becomes bigger in this dimension or in this dimension, then IS goes up, which means for a given base emitter voltage, it will have a higher current. That's all. So we don't have to worry about these other factors here. Okay, so this relationship is very interesting. It says that IC is an exponential function of the base emitter voltage. So, but I also have another voltage here, VCE. All right, so let's go ahead and plot IC as a function of VBE. IC as a function of VBE. So here's IC as a function of VBE. Well, it's an exponential, so it goes like this. But in this test, what am I assuming about the collector emitter voltage? So therein lies the difficulty with three-terminal devices. With two-terminal devices, we had only one voltage and one current. But here, we have two voltages and several currents. So when we are varying something, what are we doing with the other stuff? That's very problematic. So what we need to do to avoid any confusion is when we are varying one of these voltages, we keep the other voltage constant. We do not change it while this one is changing. So in other words, when I construct this plot and I change VBE from maybe 0 to some value, my assumption is that this VCE is constant. How much is it? Well, it's sufficient to guarantee operation in a forward active region. Remember, we wanted to make sure that the collector is, for example, higher than the base. Or at least the base collector is not forward biased. So while VB is changing, VCE has to be constant. So remember, anytime you look at these plots, you have to remember that the other voltage is constant. Okay, so that's not too bad. That is the equation that tells us how the current varies as a function of the base emitter voltage. We still don't see where we're going, exactly how this device becomes a good component in circuit design. But again, step by step, we have to build up this foundation before we get there. All right, so let's look at a few interesting points. So how much does IC change if VBE increases by 60 millivolts? Now for this, we need to remember what happened with diodes, which also followed exponential behavior. Well, for diodes, we said, if the voltage across the diode changes by 60 millivolts, the current through the diode changes by 1 order of magnitude, by a factor of 10. So it's the same thing here, because we have the same equation. So that means that if the base emitter voltage changes by 60 millivolts, wherever you are, you're here, we increase by 60 millivolts, you're over here, we increase by 60 millivolts, the current changes by a factor of 10. So we say by 10x. So the current changes by a factor of 10. That's good to remember, because just like diodes, this tells us that for typical current levels that we have in practice, the base emitter voltage of the device is pretty well known. Again, somewhere in the range of 700 to 800 millivolts for silicon devices. So if you see a silicon bipolar transistor in some circuit and its base emitter voltage is 500 millivolts or 400 millivolts, that would be very surprising. If the base emitter voltage is 1 volt, that's also very surprising. Something must not be quite right if that is the case. So it's always good to remember the range that we would have for VBE. Okay, so the other interesting result that comes out of this is as follows. Remember in diodes we said we typically neglect this 1 because this exponential has to be so large that this 1 is usually negligible. Why do we say that? Well, remember that IS is a very small number. IS is, for example, 10 to the minus 15 minus 16 amperes. Okay, so we want to go from 10 to the minus 16 amperes to, for example, 1 milliampere, a typical current that we have in practice. This is 10 to the minus 16. This is 10 to the minus 3. 10 to the minus 16, 10 to the minus 3. So what can we say about this? This has to be 10 to the 13, 10 to the power of plus 13. So it's a very large number. Now, if this is a very large number, obviously it is this exponential that is a very large number, which means this minus 1 is very safely negligible. So from now on in this course, we assume that this one is negligible unless we really need to include it. And that means that I can write, so in most cases, we have IC approximately equal to IS, exp of VBE over VT. And if I just turn this around, it says that the base emitter voltage is equal to VT log of IC over IS. So we need to memorize both of these equations. These are extremely critical equations, and we have to memorize both of them. You have to be comfortable with both equations. Okay, so that's what we need to keep in mind. And now let's go ahead and look at an example. We double the area of a transistor, and by that we mean bipolar transistor, and decrease its base emitter voltage, by 60 millivolts. What is the change in the collector current? All right, so I have a bipolar transistor like so, and I double the area, this cross-section area through which the current flows. I make it twice as large, but I reduce the base emitter voltage by 60 millivolts. So when we double the area, IS goes up by a factor of 2, IC wants to go up by a factor of 2. But when VBE goes down by 60 millivolts, the current wants to drop by a factor of 10. All right, so we say IS exp of VBE over VT goes to, this is the old transistor. The new transistor has twice the IS because the area is doubled, and its current is now exp of VBE over VT exp of minus 60 millivolts over VT, because I reduced VBE by 60 millivolts. That's the new current, that's the old current. So how much is that? Well, this we know is 0.1. Every 60 millivolts changes the current by a factor of 10. So that means that the total current is equal to 0.2 IS exp of VBE over VT. The conclusion here is that this type of manipulation of the device, dimensions and base emitter voltage, gave us a factor of 5 reduction in the current. Is that exciting? Not really. We're just trying to get comfortable with the device. Okay. So, now that we have looked at this characteristic, we need to ask one more question. In the test that we performed here and plotted here, we changed the base emitter voltage and kept the collector current constant. The collector emitter voltage constant. So the collector current became an exponential function of the base emitter voltage. All right, so we will perform another test, because this is a 3-terminal device. We had a voltage here, we had a voltage here. We kept this voltage constant and changed this voltage. Now you can ask, well, what happens if this voltage is constant and I change this voltage? So let's do that. So we say IC versus VCE. So what we're looking for is the following. We have IC versus VCE. And of course, VBE is constant. So we write here, so that we don't forget, VBE constant. The question is, what does it look like as VCE changes? Always staying in forward active region. So VBE is some amount. We picked VBE to give us a forward bias junction here. And then we started changing this voltage from here to here. This voltage, for example, is going up. We started at some comfortable value. It's comfortable to make sure that this junction is reverse biased, for example. And then we just keep going up. As this goes up, we still have reverse bias. But then the question is, what happens to IC? So I will give you 90 seconds to think about this, and just from the structure of the device and from our observations, predict what IC, how IC changes. All right, so what is your prediction for the behavior of IC as a function of VCE while the base emitter voltage is fixed So this is fixed, and we're just increasing this. Well, going back to the physics of the device, we remember that the electrons that start from the emitter and cross to the base are really determined by the base emitter voltage. So our intuition says that when the collector voltage goes up with respect to emitter, we shouldn't affect the flow of electrons here. These electrons are flowing this way, and some holes are flowing this way because of this forward bias junction, this forward bias that we have applied across the junction. So we should not see much effect from the voltage up here. So to the first order, what we should see is a constant value. So even though we are changing this voltage, this current is not changing. In other words, the current flowing through the collector is a strong function of the base emitter voltage, but apparently not a function of the collector emitter voltage. So that's a very interesting property. And again, this is the trouble with three-terminal devices. We have two types of voltages, and we have to change one while the other one is constant, and then see what happens to these currents. Okay, so let's draw that circuit again and see what we have obtained so far. Here's what we have. We have a constant base emitter voltage, as I said before, and we applied a variable voltage. So usually we draw variable voltages by a circle, so VCE. And as this variable voltage went up and down, this current didn't change. So this current is constant. So let's go ahead and place this whole circuitry inside a box. So let's place this inside the box. How many terminals does this box have? It had only two terminals, one here, one here. So, and the behavior is interesting and familiar. The behavior is, I have a two-terminal device, and when I change its voltage, the current doesn't change. What do we call this? Remember from basic circuit theory? If we have a two-terminal device in a black box, and we change the voltage across it and the current doesn't change, we call that an ideal current source. Do you remember that from circuit theory? So as far as what we can see from here, this box acts as a current source because it has only two terminals. There's some stuff going on inside, we don't know, but as far as these two terminals are concerned, it's a current source because this current is constant as a function of the voltage across it. So we say that this circuit, this black box, is equivalent to, let me erase these straight lines here. We say that it's equivalent to a current source. And we say this dashed box is equivalent to one current source. And the value of that current is IC, however much IC we found before. IC is given by, for example, this equation. So that's the amount of IC. We have, for example, 1 milliamp of current. It's a current source. So that's interesting because what we are familiar with in our daily lives are voltage sources. The battery is a voltage source. Even an adapter that you hook up to your laptop is a voltage source. We have rarely seen, if at all, any current sources in our real life. And this is an example of a current source. So the beauty of a transistor is that it can act as a current source. As we can see here, the current is constant as the voltage changes, so that's a current source. Of course, provided that we stay in forward active region, provided that this junction is reverse biased, or at least not forward biased, and this junction is forward biased internally. Okay, Now let's perform one more test. I plotted IC as a function of VCE in this situation, and I got a flat line. Now, can I repeat this test with a different value of VBE? For example, VBE was 700 millivolts. Now I change it to 720 millivolts, so 750 millivolts. Then what do I get for this flat line? Well, I get a different flat line, but at a higher value because the base emitter voltage has increased. So I may get something like this. So in that case, we have one VBE for this guy, another VBE for that guy. In a sense, we're trying to reflect the effect of both this voltage source and this voltage source on the device. And it's clearly visible. So, for example, I can say here that VBE is equal to 720 millivolts. And here I can say VBE is equal to 700 millivolts. So for each of these plots, VBE is constant. But once we're done with one plot, we can change the VBE to a new value and then create a new plot. So that tells us that by changing VBE, we can have different current levels. So if you want to buy a 1 milliampere current source, all right, you just take this box, pick this VBE to be some amount, maybe 700 millivolts. Now, if you need another current source or a different value for the current source, you just need to change this VBE to a new value that will give you a new amount of current for the current source. All right, so far so good. Now, another interesting observation that comes from our studies so far is that the collector current of a bipolar transistor is a function of the base emitter voltage, so it's dependent upon the base emitter voltage. And if we are calling the bipolar transistor a current source, and its current can change from here to here according to the base emitter voltage, we can say that the bipolar transistor is a voltage dependent current source. It's a current source, as we saw. It is voltage dependent, as we've seen before. So it is a voltage dependent current source. So that's very interesting because we were looking for a voltage dependent current source, if you remember. We wanted to build an amplifier, and we thought if we had a voltage dependent current source, we could build an amplifier. So that's good. So we can say that a bipolar transistor acts as a voltage dependent current source. The voltage is the base emitter voltage, and the current is the collector current. I hope that's clear, right? It is this base emitter voltage that defines this current. We saw that the collector emitter voltage doesn't have any role. It keeps the current constant. But if you want to change the current, if you want to create a voltage dependent current source, then this is the voltage that the current depends upon, and this is the current. All right, so that tells us that perhaps a bipolar transistor can be used as an amplifying device, and we will get there soon. But let's make sure that that's clear in our mind, and we'll talk about one more topic before we get to try to make the bipolar transistor an amplifier. All right, the next topic that we want to look at is what we call terminal currents. The currents that flow through the collector, through the base, and through the emitter. So let's talk about that a little bit. It's not that difficult, so we can fit it in here. Let me change the color of my pen to maybe this. So we'll talk about terminal currents. Okay, so we would like to find the collector current, the base current, and the emitter current. Collector current flows through the collector here, base current flows through the base, and emitter current flows through the emitter. Now, we already have the collector current. That's the equation that we had for the collector current, so we wrote it a number of times. So that's easy. So we write IC equals IS approximately exp of VBE over VT. So in other words, to characterize this three-terminal beast, what we do is we change these voltages, not at the same time, and we monitor, we measure the currents that flow through these terminals. That's the only thing we can do. We have voltage and current as electrical quantities. We don't have anything else. So we have to change these voltages and measure these currents. And so far we have done that for the collector current. We changed the base emitter voltage, measured the collector current. We changed the collector emitter voltage, measured the collector current. So that's good. But, and in fact, that's the most important current. But let's just make sure that we have everything under calculation. So how about the base current? This guy here. Is there a current here or not? Okay, well, let me draw the structure again so that we remember how this works. And then we will, actually I have it here, I don't need to draw it. Let me just show you from this diagram here. Remember what was going on in the forward bias junction. We said that we have a lot of electrons crossing from the emitter to the base because the emitter is heavily doped, and then some holes going from the base to the emitter. So maybe for every 100 electrons that go upward, we have one hole that goes downward. Where does this hole come from? It has to come from the base. This is a forward bias junction. So these holes have to come from the base. So they create a current in the base. In other words, the current that the base supplies to the transistor provides these holes that will eventually cross the emitter and go back to the negative terminal of the battery. Now, if you think about it very carefully, you might also come up with another mechanism that requires more holes from the base. Not just for holes to cross over to the emitter, but also for holes to sometimes recombine with these electrons. They're not a whole lot, but sometimes one of these electrons falls into a hole. One of the holes wants to fill up the hole. Remember how the hole appears in a semiconductor. So these electrons that are trying to carry current from emitter to base to collector, sometimes in the base region, fall into a hole, and then they cannot conduct anymore. So we really have two sets of holes that we have to provide. We have to provide some holes to cross the emitter terminal, and then we have to provide some holes for recombination with electrons. In any case, there is a current here that has to provide these holes, and that is called the base current. Now, the key to our formulation is to recognize that however this device is operating, the number of holes that are going into the base must be proportional to the number of electrons that are going this way. Because if we have holes going from base to emitter, we said for every 100 electrons we have one hole, for example, right? So the number of holes is proportional to the number of electrons. And same for recombination. In other words, we can say that the base current and the emitter current or the collector current are proportional to each other. And that's the key in writing equations for these quantities. So what we know is that, for example, the base current is proportional to the collector current. Now, of course, the collector current is much higher than the base current because we have all these electrons going this way, but they are proportional. So if they are proportional, we can come up with some factor, some proportionality factor, and use that to relate the collector current and the base current. So let's do that. Because they are proportional, we can say that IB is proportional to IC. IB means the base current, IC means the collector current. And so what do we do? Well, it's common for our notation to write it like this. To write actually IC is equal to beta times IB. You don't have to write it like this. You can write it the other way. You can say IB is equal to something times IC, some factor. But we usually write it like this. So of course, these are still proportional. But beta is now a number greater than 1. In fact, much greater than 1. Because we said for every 100 electrons here, we have like one hole here, right? So beta is maybe about 100. In practice, it's somewhere between 50 to 200 approximately, but it depends on the type of the transistor itself. Beta has a name. We call it the current gain of the transistor. So we call this current gain. Why? Because it says that if IB is, for example, 1 microamp and beta is 100, then IC is 100 microamps. So if we have 1 microamp going in here, we get 100 microamps here. So there's a gain involved. There's an amplification involved. So that's why we call it current gain. For 1 microamp into the base, we get 100 microamps in the collector. So that's great. Okay, so we found the base current in terms of the collector current. So IB is just IC over beta. We found one of the terminal currents, this one here. So we have the collector current according to this equation. We have the base current, which is just this divided by beta. So we can write IB is equal to IS over beta exp of VBE over VT. That's easy enough because we know IB is 1 over beta times IC. Okay, the last terminal current we are curious about is the emitter current. Now, should we assume the emitter current goes this way or does it go this way? It doesn't make that much difference, but our general convention is to go this way because we like positive currents, the conventional current. So this is a positive current because it's made of holes. This is a positive current because electrons go that way. And then this is a positive current going downward because electrons are going that way. So we will denote this as IE. And how do we calculate IE? Well, we say if you put all of this in a black box, then it still has to satisfy KCl because charge cannot disappear. So let's try to do that. We have this in a black box, and we know that this is IC, and this is IB, and this is IE. So I can write a KCl for all of these three, right? I can see that IC plus IB is equal to IE. So IE is equal to IC plus IB. And now, because we know IC is beta times IB, that becomes very simple. So I can write this as beta plus 1 over beta IS exp of VBE over VT. So that's the nice little equation that we have for the emitter current. So how different are the collector current and the emitter current? Not much different, because we see that the collector current is just Is x above VBE over VT. The emitter current has this factor, beta plus 1 over beta. For example, if beta is 100, this is 101 over 100, very close to 1. So we often assume that the collector current is approximately equal to the emitter current. This current and this current are very close to each other. It's a very good approximation in most cases, and it greatly simplifies our work. So from now on, in most cases, that's what we will do. All right, very good. So we found the terminal currents of the device. We have simple equations for them. You can see that all I need to know about this device is its Is value, because once I have Is, I have everything else. Vt is known, 26 millivolts as room temperature. Is is a value that is given to me from the data sheet of the transistor. And then we have values that we apply from outside, base emitter voltage, etc. So we also need to know beta if we are curious about the base current, and in some cases we are, so it's good to know beta as well. So when you take the data sheet of a bipolar transistor, the first thing you will see is Is, and second you will see is beta. Okay, very good. We have covered these basic concepts. Let's just look at an example to get comfortable with things before we go over to the concept of biasing. So here's an example, just to play with some numbers. So a bipolar transistor has a collector current of 1 milliamp and Is equals, I think I assumed 10 to the minus 16 amperes. All right, so I have biased the transistor in forward active region. I connected those voltage sources to it. So we have something like this. We have applied these voltages. And what we observe is that the collector current is 1 milliamp. And the data sheet tells us that Is is 10 to the minus 16 amperes. All right, so what we would like to find out is this base emitter voltage. So how much is VBE? So this pen goes crazy sometimes. How much is VBE? So we know the collector current, we want to find the base emitter voltage. Okay, well, remember the equation that goes like this. VBE is equal to VT log of IC over IS. Of course, I do need to specify at room temperature, because this is a function of the room temperature, and actually the temperature. Actually, this is also Is a function of temperature, because Ni squared was a function of temperature. But anyway, so I have the value of IC, 1 milliamp. I have the value of Is. Vt is 26 millivolts at room temperature. I can plug in the numbers here and find out how much base emitter voltage is necessary. And the necessary base emitter voltage is 778 millivolts. So 778 millivolts. Okay, so that was easy. Now, let's suppose that we are also given the value of beta. So we are given beta to be 50. then how much is the base current? So we are asked to find the base current, this current here. How much current flows into this base? Well, we remember that the base current is the collector current divided by beta. So we say IB is equal to IC over beta. And 1 milliamp divided by 50 is 20 microamps. So that's the base current. Not that exciting. Okay, very good. So we have gradually acquainted ourselves with the bipolar transistor, and now that we know it is a voltage-dependent current source, we would like to go and build an amplifier using a transistor. So let's do that. Let's see if we succeed in building an amplifier. I will change my pen color to maybe brown. All right, so I say let's build an amplifier. So remember how we did that last time. We said if I take a voltage-dependent current source, I1, that depends on a voltage V1, and its dependence is K times V1. So if I take this voltage-dependent device, put it in a black box, if I can buy something like this, and then I come along and connect it to a resistor, RL, and I drive this with a voltage source. For example, my voice that goes through this microphone. So that is the input to the amplifier. This is the output. And we saw that V out, after we did the calculations, is equal to minus K times RL times V in. And we said, well, if KRL is some respectable value, 5 or 10 or something, then V out is an amplified copy of V in. So the voice signal comes from the microphone, goes through the amplifier, and comes out larger, with a larger swing. So that's great. Now that we have a bipolar transistor, why don't we replace this thing with a bipolar transistor and see what happens? All right, so here's what it is. I take a bipolar transistor because I know that this device operates as a current source. It draws a current that is an exponential function of this voltage. So that's a voltage-dependent current source. It's exponentially dependent, which is rather diabolical and strange, but that's okay. For now, that should be fine. So let's do this. Here's our voltage-dependent current source. Again, I'll draw a box around it so that you can see the correspondence. And then I apply my signal. So I will draw a microphone, assuming that the microphone is applied to the amplifier. So here's the symbol for a microphone. I don't know, maybe something like this. So we will call this mic. That's the microphone. The microphone has two wires, and the two wires are connected directly to the base and the emitter. And then we connect a resistor on the side, just like before, RL. And now we go ahead and measure this voltage. So I'm hoping that as my voice goes to the microphone and generates a small, weak signal here, this transistor will amplify it, will deliver it to RL, and like before, we get something large at the output. So let's see if that works.